Hello, everyone. So this is Varuni here. I'm part of the data science group team here at the ALCF. So as part of this hands-on session, um, the plan is to introduce you to the different novel accelerators here at the ALCF that we house. I know in the morning, you saw that each of these um, systems were introduced to you with respect to the hardware and the software stack. Um, and really, the goal of this session is to basically get you a hands-on on these systems and how to um, have an experience of end-to-end workflow on this particular systems. Really, I'm not aware of the kind of audience here. I don't know if it's your first time, haven't seen the systems before, haven't been accessing any of these systems. It's a good introduction for you to learn more about it. But if you have already seen this or worked on it before, bear with me, and probably this is like a refresher for you, and then you can get your applications ported as soon as possible, hopefully by the end of this session. So
just to give you a framing as to what you're looking at as far as audience, we have somebody who's this is his very first time working with LLMs, all the way up to somebody who is trained in the foundation model on Cerebras. So you got the whole spectrum.
Okay, sorry, I'm not really able to hear well. There's a lot of noise in what I get, but hopefully people are okay to start get this introduced to these systems, is what I hear.
Yes.
Okay, thank you so much. So let's, first of all, before just getting onto each of the systems specifically, I just want to give I want to show you some of the links that are probably useful to follow during this hands-on. I really would encourage folks there to actually, follow through as we go through these material, if possible, and you have access to these systems and have accounts on them. So for this tutorial, we've put together a GitHub repo. And it's part of the Summer School 2024. And you can get all the materials that's required. Honestly, since LLMs are the state of the art today, so we will be just focusing mostly on the different LLM models and how to run them. But we will also, as a part of the process, show you the documentation and links to basically even include other models as such. So this is one place where we've just put it for this tutorial. But then at any point of time, if you go to the ALCF website, you have an entire website that covers, of course, Sam spoke about the Polaris and the other systems, but specifically all the information that's required for the AI testbeds are under this particular link. And you can always look back at this at any point of time of your convenience and go through like what are the different systems, kind of the overview of the system and how to really get started, how to log on to the systems, and so on. And also, especially one important is like you see how to set up a virtual environment on these system and really get the environment working. And you also have like different, small examples to even running the large LLM models, and really all the good links that you would be, you would find it helpful while working on these systems. So having said that, I think we can get started onto our first system, which would be the Cerebras. Even before getting onto the system, again, here is the open source document of Cerebrus, systems as such, and you can have all the, porting guides and the model zoo attributes and everything here. But really, let's really get started on the system, and that is specific. So let's cover what is specific to the CS2 cluster that we have in Argon. So if you go to the Cerebrus folder, you will exactly have how this a CS2 cluster looks like here at the ALCF. So here you would have a local machine and you log on to these login nodes using the cerebrus.alcf.anl.gov. The username is your specific ALCF account that would have probably been generated by now. And then you log into one of these login nodes. You can directly do it, but if you don't and just gives the Cerebrus, and then it'll randomly put you on to either of these three nodes. So the password used for this is the mobile pass plus password. So it gets generated. It's like a multi-factor authentication. I'm hopeful that this is set for you already, pretty much similar to any other systems like Polaris. So you land on these login nodes, and then from there is where you actually initiate all your jobs. So Cerebrus specifically use their inbuilt Kubernetes to actually schedule your jobs so that two users are not bumping into each other and accessing the same CS2 cluster. So the CS2 cluster, of course, has both the management node as well as the other CS2 wafer scale engine. So yeah, so let's get started here. I will be going back and forth on the terminal, which probably might be annoying, but hopefully you can use it to follow with me. So we just log in to the Cerebrus system. Bear with me for a second. So this is where we end up on the login node. So from here, the first step is to basically create a virtual environment for Cerebrus. So here are the steps basically to perform to get a PyTorch Cerebrus system working. Cerebrus basically supports most of the PyTorch support. And so to do that, let's have a and then you create these. So the current software version that we have on the Cerebrus is the 2.2.1 version. So these are all published basically on the ALCF website that I showed earlier. So that documentation will be always up to date. So once this is done and you're still wanting to access the system, kindly refer to the latest guides on the ALCF website. So yeah, sorry. Any questions from the audience? Okay, hopefully not.
Nope, we're following along. Things are going well.
Awesome. Yeah, just be louder in case you want me to stop at any point of time. So yeah, the Cerebrus, software requirements are all present here at the software, and you can create this virtual environment here. And you just type create, and you launch all the software packages that are required for the Cerberus PyTorch is bundled up here. So it'll probably take some time to install all the required packages and wheels. So I guess I have that already here, which I pre-did before the tutorial started. So you can also clone the Cerebrus model zoo repo, which essentially looks like this. This is the open sourced model zoo repo that is maintained by Cerebrus. So if you go through here, and mind you, all these links are present again in the summer school GitHub repo. But if you look at these model zoo links, you will be able to see what are the different kinds of models that are currently supported. So you see the multimodal, the large language models are inside the MLP. Then you have vision as well. I think currently vision is only support is for through DIT and VIT. But if you see the MLP, you have a bunch of different models, mostly that stems from the GPT-2, GPT-3J. You have the latest Llama, Mistral, and so on. And you have, good support for BERT, Bloom, and DPO as well. So actually, it encompasses a huge range of language models here. And I really feel the best way to get started is pick up one of these. Probably we would be working with some flavor of these kind of models today, and just get your custom data set, patch that into the scripts, and you should be good to go on the system. So having said that, so if you just git clone that repo in the terminal here, let's just go through how to run the GPTJ model. Um, as an example. So you get cloned this, and you are currently at release of 2.2.1. And if you refer to this GPTJ, this just provides you to all the steps that are required for running the GPTJ model. So just a refresher for everyone. So most of these systems have two steps before you can, or as part of your training of your models. One is first the compilation process. So once usually you have either separate commands to compile your model and generate the compile artifacts for the model so that it runs on the compute nodes, or sometimes it is like for Cerebrus, it's both put together. So just using the run command will initiate both the compile as well as the run command as well. So as part of this, so we are here at the GPTJ model directory. We have sourced the environment. So one important aspect is any model specific packages are all present here, the model zoo requirements.txt. So if you just kind of run them, it installs all the required packages here for you. So Yeah, I can do that here. Which probably takes a little more time. And so yeah, we just have provided a sample YAML file. This is the config file, which we will take a look at it. So usually all the parameters which is required for your data through the train input or the eval mode, and your model parameters, which, as you can see, most of the vocab size or any number of the hyperparameters that you want to specify, and the initializing stuff and all the precision and the optimizer. So all of these, and of course the run config too, all of these configurations and any kind of interface to the models are being done by the YAML file. So each of the model that you run requires a YAML file like this to be specified. So each of these models, if you go through them, will have like a configs directory, and you'll have some bunch of YAML files. Like for example, it can be 6 billion model may have one, or an EOX model will have separately. So you can really specify or tweak this kind of YAML file to suit your requirements and preferences. But the best way is to go through each of the models and pick up one of the config file that they have and probably modify from there. So I've just modified the one that comes actually from the repo, just to use here the training data. So this data is available for consumption, but in case you want to have your own custom data, which is in usually the HDF5 format, so you can tweak this and provide your own data set. And you can also use the other configurations or change it depending on your requirement. So all the changes that has gone into this is basically for the training, I'm using a different data set that's housed on the storage here. So once you are prepared with the environment, you have source the virtual environment. Now you have the config spec ready. So all that is required is actually just set the model directory that you want. And mind you, all these have to run from the parent directory of the models. So I'm currently running here at the GPTJ, but in case, say you want to use Llama, then you go to the Llama and then initiate the same commands pretty much, and just follow the same process that we did, and you initiate from here. So GPTJ. So yeah, all that is left is we just export the model directory. And this essentially is the command used for running. So if you see here, the Python, it's just the run.py, which is the entry Python script that's essentially called. And then you just use the CSX, which is the CS2 wafer scale engine that you want to specify. Just name the GPTJ, the name that's optional to you. And of course, this is of very essential, which is the params or the YAML file that we just you know tweaked to have the data set. And then this is here is the number of CSX that you want to specify. Currently, we have like 2 CS2 clusters. So this particular command uses both the CS2 clusters that we have. But then, of course, you want to choose based on your requirement here. And in this particular thing, we use a mode for training. You can change it to eval if required, and you provide the model directory. So this model directory is specified where, because once you go through the compilation process, the compile artifacts are essentially dumped into this model directory. So assume that you have once compiled and you're not changing the YAML file pretty much for any of the model parameters, and assuming those aren't changing, like your batch size or your embedding size, and so on, then you don't have to recompile your models. You can use the pre-existing models, and your runtime would be faster. um, yeah, but assuming you are changing some essential parameters of those, then of course it'll recompile for you. And then of course the mount directories, these are the mount storage mounts, that is essential, and the Python path is providing to the local directory path that you are running your code from. Um, and there's another compile directory, which, there are some temporary artifacts that will be produced as part of the run. And then, of course, this you're just logging to the different um, log file. So that, oops. Okay. So the reason here that it did not go through is I had already run it, and it had produced this model directory GPTJ, but that ran for, say, 200 steps. So the way to, go about it now is, say, if you use the configs and then the GPTJ 6 billion sample, um, you go through the max steps, and in case you want to probably now increase it to, say, 800, and if you relaunch the command, uh, I think it should work fine. So just for the interest of time, I will go through one of the already existing run that we had earlier, and just, kind of go through how the log file will look like. NLP, GPJ. So essentially, you will see that these are, the different batch sizes that it'll be running on. And sometimes if you choose to, for the stack to determine by automatically what's the best gradient accumulation and the micro batch sizes, so it'll do that. And finally, once that is done, it'll show the compilation was successful. And then you program the Cerebrus cluster, and then you essentially start training after you stream the weights, the initial weights. And then you can see a bunch of, and because we're using, say, two CS2s here, we have the data pipelining here, and then you stream the input. And then this is the indication that it's going to start training. And these are the two, epochs or the steps where the logging is enabled for these. So it trains here, and you can see the log, loss is just changing, and so on and so forth. And this just, was a test run for just, I think, 200 steps. So yeah, at the end, you'll see that it'll give you the total number of samples it processed and the total time it took for, you know, the entire run.
This is really straightforward. It's a great solution here. Just as a question,
Yeah.
how is it like determining the micro batch size and the gradient accumulation steps? I have it running on my machine right now, and I can see it's doing this like exploring 4 point, exploring the data layout. So what is that?
So this is from the internal stack that happens. There is a way to switch it off, and you can just specify the one that you want. The way to do that, I will put in the chat. It is to use, I think, use CS2 or CS gradient accumulation set to false. And also you can just specify the micro batch size. But this essentially just is a way to like get the best performance out of the system. So naturally, depending upon the model size and the different configurations, it will kind of try to set the right gradient accumulation and the batch size, micro batch size. But then you can see here that so the models so usually is shipped with the best batch size or micro batch size or the different parameters of the model actually, um, or especially these kind of hyperparameters, which is probably tried and tested at the Cerebrus, and then mostly they give you the best performance. And as you can see, like after doing all this bunch of things, it just said no benefit from the gradient accumulation expected. So it just falls back to the default one that is set. Um, but yeah, I'll update you the way to just turn it off so that it's just faster.
Thank you.
No problem. Yeah, so that's pretty much on the Cerebrus, and any other model can be, run just as, just the way we did. Most of these, arguments will remain same. So if you just go through the entire model, so you'll see that run.py is the essential first Python script that will be invoked for any of the models. But only the things that will change are probably the parameters and the name of your uh, kind of model that you want to train and so on. But otherwise, most of these are going to remain constant. And also I think so some of the jobs, if you want to like know what are the different jobs that are running on the system, so you can use this particular command, which is csctl get jobs, and you will see that my job is queued, somebody else is running, so you can know if somebody else is using the system. You can kind of get a hang of whether your job is started yet or not. And there is a way to also look at some of the measure parameters from this Grafana page, which you can inspect by tunneling. So yeah, but I'm glad that some of the participants there have been able to run successfully on the system. I would probably stop this run because I don't want to keep others from queuing as well. So that's pretty much with the Cerebrus system. Yeah, any other information, you can always go through this website. It'll provide you some of the well-known models like Llama 7B. Again, most of these will all remain the same. Some of the data sets that you want will be already available in, say, software, say, data sets. So a lot of them are here if you want, or there can also be software Cerebrus, where you might have some of the data set present here as well. So in case you're using the system, please be mindful that your home directory is limited in space. So any data sets or any other artifacts that you want to house, it's better to go in this particular directory when you use the system. So yeah, if folks don't have further questions on Cerebrus, I think we can get started on the next system, which pretty much is Samba Nova. Again, Samba Nova, very similar to Cerebrus infrastructure we have. Like, we have a local machine that you're connecting through a login node, which is essentially this. So you just SSH with your ALCF ID, user ID, to Sambanova alcf.anl.gov, and using the same mobile pass plus passcode. So the difference here is so once you land onto the logging node, for Cerebrus, we were able to just log in or initiate the run commands directly on the login. But with Samba Nova, it just changes a bit, because now from the login node, you move on to one of these um, 8 different compute nodes you have. So you can log into any of these different compute nodes, and you can access the entire system through any of these compute nodes. So essentially, I, I know this people, might end up always using the first one, but I always encourage folks to use the different compute nodes, because assuming that you have specified in your scripts to use that particular node specifically, on which the host name that you are on currently, then it so happens that most of us just use this, and we might get queued up if some long job is running over there. Mind you, all these systems are first come, first serve. So once you have your scripts launched and you get access to, or your job gets scheduled, then it will run to completion. Of course, depending on if you don't have any errors in between. And once you relinquish your job, then some other job will take over. For Sambanova, we use Slurm as the scheduling manager. So essentially, we'll take a look at how it is used to launch your applications. So for Sambanova, I'm essentially will do the same. So here you get onto the default login node, but here is the difference where you have to SSH to you know SN30. So I choose probably R2H1 here. And now we are on this compute node. And from this, we can always launch any script that can, utilize any of the total number of nodes we have. It can use just one RDU on one node, or it can have multiple nodes based on the application needs that you have. So with Salmonova, the one advantage here is you actually get pre-built like virtual environments for each of the model. So you don't really have to specifically build any virtual environments per se, or even the default stack would be up and running. So the main source of all the apps is here in the opt Samba flow and apps. So this is the essentially all the applications that are available that are housed here. Unfortunately, you this is not available somewhere, on a GitHub repo or any other place. This is where each of them are upgraded based on the release that you have. Again, varied and diverse, applications with respect to the domains. You have the starters, which is basically very small, like your MNIST models. Then you have the NLP, speech, and then image, mostly that are important. And maybe we can take a look at the different language models that are available here. Again, as you see, you have like GPT 13 billion. Models, and most of this there are also some Geneslim, that's the science models that are available. And yeah, so most of the model specific modules and tasks are present here, and the transformers are present here. All the required functionality and the functions required for you to call are here. But there are also readily available scripts that you can use, which are present in the data ANL scripts. So essentially, if you take a look at these are like, bunch of them. There are this GPT 1.5 billion, or if you need a unit model, then there are some science application, models. And even in the NLP, you have some of the old scripts that are also available for 13 billion and 8K sequence length. So yeah, for each of these models, you can come up with the script to launch. And let's go through one of the examples so that it's more clear um, to whatever I'm saying. So assuming we want to run, say, 1.5 billion GPT model, so the scripts for that are basically as I specifically told before, that Sambanova has two steps that are completely independent of each other. One is the compile, and then you have the run commands. So just let's see through, like, of course you can. So yeah, one important aspect is, though the scripts are available here in the slash data ANL scripts, it's always advised that you make a copy of these scripts in your home directory and launch them from there, because essentially this is a this particular directory is probably only read only, and a lot of these scripts will generate some artifacts or files and logs based on the relative path. So it's always good to have something as your home directory, where, or your parent as your parent directory, so that you don't run into issues of any permissions. So yeah, just make a directory that you want to run it up from, and then just copy these, particular scripts from there. So if you go here, let's analyze some of the script. So initially it's the GP. So the first part would be the compile script. So if you go through initially, it's just like, kind of, as I said, setting some of these, name model names or the output path directory, and so on and so forth. And some of the environment variables are set along with it. And then, of course, you can have the output directory path that is specified. So this is the directory where the actual compilation will take place. And you can reuse this compilation every time you're not, again, going to change any of the essential parameters of the model. And then this is just what a compile command looks like. So as we saw that the OPT, Samba Flow apps, NLP, and this, and the transformer hook.py is essentially the starting point of these NLP applications. And you have like a bunch of arguments, but I would say, most of them are self-explanatory, in the sense you're first doing a compile, and as part of the compilation process, you end up getting the goal of the compilation is to produce a what you call as a PEF file, which is essentially the crux of the, you can say it's the graph that is produced and used to lay the SN fabric, or the hardware as such. So this, all the routing information and everything is present in this PEF file. So as a part of the compilation, this is the most important output, and you specify the name that you want it to be, and you pick this and provide it to the run command, and that's how you couple those process. And then, of course, these are the output folder, and then whichever the module name that you want to train, and usually the task name is the causal model. Then the sequence length, you can determine the batch size, and of course the output directories where you want to specify the artifacts to be as part of it. Then yeah, some of them are like the GPT tokenizer, which you want to specify. And there are also a lot of, hardware specific configuration files. These are pretty much useful to enhance the performance of the training of the model that you are looking at hand. So usually these come packaged along with the applications directory. So if you're not sure of which one to use, which basically depends on, the different parameters that you provide for your model, that'll kind of map to some of this human decisions files, which use like the total number of encoder layers it has, and all the tiling information, and so on and so forth. So this is specific to the hardware. So if you're not aware like which one to use, or you're confused, always reach out to us, or open a support ticket, and somebody will help you regarding these kind of information. Um, so so essentially this is how a command for a compile look like. And at the end of it, the PEF file, which is some PEF name dot PEF, is generated in the output directory. And then comes the run command. So essentially what you're doing is, the other file, which was a script file, which has the run command, is basically called from here. And for that, you basically use the slurm command. Here we are using the spatch. And you can use this to do some, the different data parallel tasks that you want on this machine. So it's essentially, so each of the RDU so each node has like 8 RDUs, and each RDU has, say, 2 tiles. Depending on the size of the model, it can just fit in one tile, which is like essentially half an RDU, or it can take up the entire RDU as such. So, but most of the models that small and medium-sized models probably take up to like one RDU. And so even 7 billion models easily can be packed in, like, say, one RDU. So you have here you're not doing any kind of data parallel, which essentially is by saying that you're just running it on one task. And then so you have these 8 RDUs, and this particular application can actually fit in a half an RDU, or one tile. So you can have totally total number of instances that you can have for this particular application is like 16. But in that, you just want one task to run. So this is how you specify the distributed training kind of parameters here using this LERM. And then you will essentially call this run script, which we just kind of copied along with this compile script. So you just need to launch this particular compile script along with the model parameters, and then this will in turn basically call this base single, the script which has the run command. Initially, it's pretty much, it'll look the same, all the output directory, environment variables, and so on, just to ensure that it's set properly. And you can say, and of course, it checks for the PEF file that it is looking for. And if it does not find it, of course, it should recompile if it doesn't find that. But then uh, essentially, once it's compiled, the run command pretty much looks very similar to the compile command, until probably the same hookup file is what is called. But the compile command is now replaced by the run command. And also you provide the data for you to process for the training. And also this PEF is where you specify the actual PEF that was generated as part of the compile process. Otherwise, yeah, pretty much the other parts will be as same as what you specified for the compile command. And yeah, so when you initiate this command is when the training will go through. Oops. So yeah, the way to uh, compile is you just initiate this compile script and provide, and for this particular application, the only parameter that you want to specify is the batch size. So I am providing a batch size of say 32. So you should be, and if you follow that, it'll first go through the compilation process. But as you can, and the log file is basically this. And if you open this log file, it's just some of these status of the system, and you can see that because I had compiled it previously, it is not it is not going through with the compilation. But just a quick, just to show how a compile one log looks like. This is essentially how it should be looking. Yeah, it's a little verbose. Honestly, I would not be going through the entire thing. Um, but if there is any issue, or if it doesn't compile, I think it will be self-explanatory as to why it's happening. But there are a bunch of warnings and like info that is produced. But the most important aspect for you to kind of look out is this part of the log file which says that the pef file is created. So essentially this was my output directory, and then where this pef file was created. So essentially if this pef file is there, it would not recompile again. Of course, it also based on the different parameters that you provide for the model. So once the compilation is done, the compile here is ended here. So it almost took 2,000 seconds to compile the GPT 1.5 billion model. And then you see that the run command is initiated. So once the run command uh, is initiated through the Slurm job, so that's why you see the submitted batch job of the batch number that you get. So the way to see is like you can have so you use SQ to check if any of your jobs are running. So the one that I just ran is running as part of the job ID is this. So the way to find the path of that particular log file, so any Slurm job that's initiated under your username will have a Slurm log, which essentially is in your home directory, which will be your Slurm slash your job ID name dot out. So that's where you actually find the log to your actual output of your training run. So if you kind of take a look at that, so sometimes usually it's if there is no compilation, then it'll just go through that and you can see that the training starts in the same log directory as the other. So yeah, so essentially you'll see the different logging. um, you know it logs the command, and of course there are some um, warnings which you can easily ignore. But essentially the training, yeah, so you look for the training loop that has started. I've provided like 100 iterations over here. So it'll provide you all the information as depending upon the laws, the validation loss as well, and eval info. So yeah, essentially this goes on throughout the running, and you can basically keep track of that. Um, yeah, so that's and any artifacts of that training would be say available in the data scratch directory under your of course it depends on where you have specified your output directory to be. So, depending on the different runs that you have, you'll have all these artifacts as part of this directory. Just for the um, tutorial's sake, I made a pre-compiled version of the 1.5 billion model. So you can directly reuse this by probably just setting the uh, apps, NLP, GPT. So you just can go here, single compile.sh, and say you can replace this. So initially it would be under your username, but you can always use this precompiled artifact for the output directory. And if you change that, it'll not recompile again, and you can probably get away with the compilation just to help you get through that process faster. Yeah, so that's pretty much what I had for Samba Nova. Any questions? Yeah, otherwise you'll have all the information that's and the links to the data sets, some of the scripts that I specified, the apps directory, and the Samba Nova documentation as well. Oops. Yeah, they should cover pretty much all about the hardware, software stuff that was presented in the morning, and there's some brief tutorial on or some help porting the different kinds of models. But I essentially would recommend you to go through this and really get hands-on on these systems by going through the scripts that I just showed you. That'll really give you a flavor of what things you need to change and how to tweak it based on kind of your needs. So yeah, that's it from me. The graph core and the grok part will be covered by Sid. So in case you have any questions on any of the systems, yeah, please feel free to reach out to us anytime, and we'll be happy to help.
Great. Thanks a lot, Varuni.